This chapter is kind of the first one all semester that we really are going to be discussing pressure in great detail. So I want to take a little bit of time in this video to talk more about it. So I mentioned in the video with kinetic molecular theory how gases exert pressure, but first I want to start talking a little bit about the units that you will come across. So the most common pressure unit known is atmospheres. Atmospheres is abbreviated as ATM. Another one is millimeters of mercury. Which is abbreviated mmHg. You have torr, which is just abbreviated as torr, simply. Another common one that you might see is pounds per square inch. So actually I'm just going to write that here. So we've got pounds per square inch. And then you've got kilopascals and pascals. So of course, a kilopascal is just 1,000 pascals, but sometimes you'll see pressure written in both units. So pascal is just PA. So kilopascal, hopefully you could guess, is kPa. Now, mathematically, how do these all relate to each other? Well, atmosphere, again, that's the pressure unit that you're going to use in the ideal gas law. So you're going to want to know kind of what 1 atmosphere equals in all of these different units. Now, so I'm going to put 1 atmosphere here. So 1 atmosphere is equal to 760 millimeters of mercury. Now, one thing to keep in mind as I'm saying these is that all of these can be used as conversion factors. So, for instance, if you are given a problem and you need to plug it into the ideal gas law equation, which means you need to get the pressure in atmospheres. If you're told you have 380 millimeters of mercury, well, you can use this as a conversion factor. You can say, you need to cancel out the unit of millimeters of mercury, so you put millimeters of mercury, and I didn't exactly leave myself a lot of room here, but you put that in the bottom so that the units cancel out, and atmospheres goes on top. And you've got 1 atmosphere for 760 millimeters of mercury, so you would just do 380 divided by 760, which would give you 0.5 atmospheres. So again, all of these can be used as conversion factors. Alright, the next one is going to be torr. And as it turns out, 1 atmosphere is also equal to 760 torr. So although millimeters of mercury... So another thing to keep in mind is that these could also, not only am I showing them all to atmospheres, but since these are all equal to 1 atmosphere, they can also be used as conversion factors to each other. So if you're given this millimeters of mercury, you could also say 760 torr over 760 millimeters of mercury to convert from millimeters of mercury to torr, for instance. But, of course, as you can see, that number is exactly the same, which means that even though millimeters of mercury and torr are different units, they're mathematically, the numeric values for them are going to be mathematically equivalent. So they're in a 1-to-1 ratio. So the next one is going to be pounds per square inch. So 1 atmosphere is going to be equal to 14.7 pounds per square inch. I'm going to go pascals first here. So 1 atmosphere is equal to 101,325 pascals. And as you can see, that's kind of a large number. So that's why sometimes kilopascals is used. So to convert from pascals to kilopascals, well, remember, kilo means 1,000. So there's 1,000 pascals in 1 kilopascal. So you just have to divide this number by 1,000, and you'd be left with 101.3 kilopascals is equal to 1 atmosphere. So again, those are some good conversion factors between different pressure units. I want to talk about two more concepts. So one is STP. So STP stands for standard temperature and pressure. Standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere. So if you are ever working on a problem and you are told that the system is at STP, what it's saying in that sentence is it's telling you directly that the temperature is 273 Kelvin and the pressure is 1 atmosphere. That's what being at STP means. And there's one other concept I want to talk about, because that's one that a lot of times people don't fully grasp, and that's the concept of a vacuum. So a lot of times if you were to ask someone what a vacuum is, they would say it's something that sucks things up. Which, I mean, it makes sense that they would say that, because the only time we ever really encounter something called a vacuum in our everyday lives is when we're, using a vacuum cleaner. But that's not actually what a vacuum is. That's a side effect of a vacuum coming into contact with an area that's not a vacuum. But the actual definition of a vacuum is that it's an area with absolutely no matter. So absolutely no atoms, no matter, not even air, nothing at all. No matter of any kind. And since it has absolutely zero matter, that means there's no gas. So it has, and thus, no pressure. So it's an area that has absolutely zero matter of any kind, not even gas molecules, not even air at all, and thus there's zero pressure. So, of course, when an area of such a low pressure, no pressure at all, in fact, comes into contact with an area of high pressure, the high pressure is going to kind of really quickly rush into the low pressure, and that's kind of the concept behind vacuum cleaners. But keep in mind that if you hear that something is a vacuum, what that means is that the pressure is zero, because there's absolutely no gas of any type.